Welcome everyone. Welcome to Scaling Data in the Cloud here at Cloud Slam in 2011. My name is Frank Weigel. I'm the Director of Product Management at Couchbase. And we're going to talk today about how we can best scale the data layer in the cloud. I should remind you that for the question-answer part of the session, you will find on the right side of your WebEx session a Q&A panel. Please select all panelists in the drop-down there to ask any questions, and I will get to them at the end of the presentation. Equally, should there be any other things coming up during the talk, or you have trouble understanding if the voice connection is bad, please let me know in the chat window. Equally, select all panelists there to make sure I can see your message. Thanks so much. So, why choose the cloud? I'm sure all of you are here at Cloud Slam because you already are in the cloud or you are interested in putting data in the cloud. So let's quickly just review the obvious advantages that you get from being there. The agility that is gained is just enormous. The speed of provisioning and, of course, the capabilities to expand very rapidly is something that is unmatched when it comes to more traditional data center models, of course. As a result, the availability goes up with the redundancy that becomes available. Machines can be repurposed very quickly by simply reprovisioning them with a different image. And, of course, ultimately, it leads to a lot of cost saving because you're paying for the capacity you are actually using, and there's no capital cost to buy the machines. Great advantages, and I'm sure those are some of the key reasons why all of you are looking at the cloud. But as we know, if there are advantages, typically there are some resulting properties that might be less desirable. And of course, in the cloud, this means that now your environment is made up out of lots and lots of nodes running on somebody else's infrastructure. As a result, things like partial network outages become much more likely, meaning that some nodes can't communicate with some other nodes in your system anymore. Even complete node failure, of course, does happen. You also are limited in what kind of resources are available to you on a machine. For example, SSDs or Fusion I/O and other proprietary technologies are not typically available in cloud systems. So when it comes to your I/O capacity, you typically are somewhat more constrained compared to your own machines. Equally, the amount of RAM available or the CPU capacity is equally typically somewhat below what traditional data centers could offer. So as a result, it's all about using the available nodes resources very efficiently and having solutions that are specifically tailored to fit that model, of having lots of equivalent nodes that can easily be added and removed, but have to cope with the potential failure of nodes at all times. And that's really what scaling data in the cloud needs to address, and that's what it's all about. So let's look at a typical stack that is used for most solutions that are deployed in the cloud. Typically, there's a presentation layer, meaning the part that is ultimately displaying the results. So most of the time, this will be a web browser where your customers or users are online looking at some output. There is a tier of application servers, meaning for example, it might be a application server in Java, or it might be a web server, some layer that serves other content. And then underlying this is really the key layer we're going to focus on, which is the data storage layer, because then, of course, all the application responses, all the application output typically is dependent on state, on data that is stored in the data storage layer. Now, scaling the application layer is a very well-solved problem. For example, scaling across web servers is something that is done very, very commonly. It means typically there is a load balancer in front of a tier of identical and identically configured application servers. An incoming request from your browsers or from the presentation layer is routed to one of the application servers, and all application servers are identical. They will serve out the result. If one of them goes down, the load balancer will simply ignore this node and balance the load to other nodes. You can see how in this way you can add capacity simply by adding additional nodes. You can see how this scales linearly, and it's all around very good. Now, the thing though, of course, is that the state that the application tier needs to be kept in a central place, and that is the data storage layer. So that's where all the data is kept, which enables, therefore, the request to be served by any of the application servers, because whatever state they need to access about a request will be maintained within the data storage layer. So whether that's things like the product catalog or the top 10 friends, all these things need to be kept somewhere in the data storage layer so that they're available to the application server layer. Now, as I already said, this scales very well. You can see on this graph we've got the application response time in the blue and the system cost in orange, and you see that with this model you can add more application servers. The latency basically stays reasonably constant or might go up a little bit as you have more and more. You see system cost is a linear scale, and you just have a linear more and more users, meaning if you have twice the number of application servers, you can now serve twice the number of requests, and your cost has doubled. And then, of course, is the best case, so you can't be better than linear scaling, assuming your nodes are fully used. So this is a well-solved problem. The problem is on the data layer and scaling that. So let's take a little excursus and look back of where these traditional databases are coming from and what they were designed for, because that shows why it's difficult to use them in those scenarios. On the left here on this nice chart, we've got when relational databases were invented, the landscape or the problems they were designed to solve were very different. The number of users of systems was much, much smaller. A few thousand users was as big as systems were designed to do. Today, of course, 2,000 users at the same time, 2,000 concurrent users is considered very small for many online applications these days. Back then, populations and data was much more static. It was about highly structured data, meaning you had the whole concept of a schema. That is, of course, one of the fundamentals of traditional relational databases. Would apply very well, right? You had your ticketing system, or you might have your data, your credit card transaction, and those things had certain fields. They had to be there, and those wouldn't change over time. It was very structured. It lent itself extremely well to the relational model and static tables and static schemas. Back then, you typically had a centralized infrastructure, of course. There might be one mainframe that was accessed from everywhere. Memory was very expensive. We all remember the famous quotes from Bill Gates about how much memory computers will ever need and so on. And of course, networking was very low bandwidth and not something that approached anywhere near the capacity we have today. Surely, as I was listing all these things, you immediately recognize that today's world, today's requirements are very, very different. Users exploding, hundreds of thousands of concurrent users are not that rare anymore. Even only mildly popular games will have happily tens of thousands of concurrent users at any point of time. The user population will change very rapidly, new users coming, old users never coming back. The data has changed. Rather than highly structured data, these days, much of the data just isn't that well structured anymore because it depends on what is available. Different data might be available for different users or about different users. Applications evolve rapidly and you want to capture new information suddenly, but you don't have the luxury or the ability to go back and update all existing data sets to fit a new model or a new schema. High-speed networking, of course, is common. Even our phones today can provide quite a substantial bandwidth compared to 1975. And of course, memory has also gone down dramatically in price. So therefore, the requirements have changed, both on what's available as well as on what the problems are that need to be solved. And really, that's why the existing relational databases have this problem, because they have separate tables where they need to lock multiple columns and rows depending on the operation. There's a lot of lock contention happening, meaning that one axis will interfere with another axis. And so as a result, one machine can only do so much work, of course, so you can put a bigger and bigger computer there, but at one point you've reached the maximum capacity of that computer. You can start to go to clustering relational databases like Oracle RAC and so on, but despite them being primitively expensive, even they don't scale out very well. Once you've reached a certain number of machines, often around 6 or 7 machines, you'll find that because of increased lock contention and overhead, even adding more machines won't actually let you serve more users at the same time with low latency. And as a result, you get a cost curve as you see on the screen just now. You can see that the system cost explodes and the response time goes up and goes up until it reaches a point where no matter what you do and how much more money you spend, you basically can't serve more users. And that is a problem. It's a big problem, and it's a problem for many types of application. Now, this is where the NoSQL movement really has come in. And as you will see, it's basically about trade-offs. It's about giving up some of the properties that RDBMSs have, like, for example, transactions, so being able to do multiple operations as one transaction and having the asset guarantees to be sure that you basically do all of them or none of them and so on. Those things are great for certain things like credit card transactions, but they're not required for much of the new data. And once you're willing to give up some of those constraints, then suddenly you're able to design a whole different type of database that is much better suited to those new types of data and that doesn't have the scalability concerns that traditional systems have. So really there are a few characteristics that are very much common across the different types of NoSQL databases. No fixed schema is definitely one of the trademarks. So unlike traditional systems where you have to define basically for each table which columns would be in a table and how they relate to each other, now you don't have schemas anymore. Applications are free to store data basically in any format. Different pieces of data in the same database don't have to have the same fields. They don't have to have the same structure. And these NoSQL systems all are able to cope with that. And as a result, your application design can be much more evolutionary and can be much more flexible to accommodate new types of data and new types of need. In order to cluster, which is typically another requirement, so the ability to add more and more machines to get more and more capacity while still retaining low latency, requires something that's called sharding. Sharding basically means that the key space, so all possible keys, somehow get divided up into slices, and slices get allocated to specific machines. That's key sharding, and typically NoSQL solutions have a way of automating that so that the user doesn't need to do that within the application. The better systems, of course, are able to accommodate servers being added and removed at runtime and still work and keep the load balanced across all the nodes in the cluster. Low latency is a key requirement for interactive applications, so most NoSQL databases have some element of low latency optimizations, even though that's an area where there are quite big differences depending on the system. Another common path is that you don't have these multi-operation transactions I was talking about, because once you start introducing that and different parts of the transaction might operate on data on different nodes, you end up with very complex locking problems that, for one thing, introduce a lot of contention, which is exactly what you're trying to avoid, and also in a general distributed environment cause all kinds of other issues if you have to be able to cope and deal with nodes failing. It means a lot of timeouts and potential waiting, all things that aren't really agreeable to the low latency and the clusterability requirements that those databases have. So, what are the key types? Excuse me. There really are two categories of NoSQL databases that are common. There are some other types like graph databases and so on, but I won't discuss those in more detail because they're less frequently deployed. At the simplest form, there is something called key value stores. A key value store really is around the simple model that there is a key which accesses a value, and the value is an opaque bit. It's a black box basically, and the contract is you give the key value pair to a database, and then as long as you know the key, if you ask for it, you will get back the exact value exactly as you've provided it to the key value store. The key value store itself does not understand, so to speak, the value part, meaning it can be anything. It could be a JPEG, it could be an XML document, it could be a JSON document. The database itself doesn't care. It won't try to understand what's inside, so to speak. These systems are typically heavily optimized to its low latency access because there is no need for parsing the values. Often they're just stored in memory, and so the access latencies can be very, very low to get this back. There are caching systems like this, for example, Memcache D, that I'm sure many of you are familiar with, which has many of the same properties, but it is a cache, meaning that if you put too many values in it, it will throw away some so that it can keep all the data within the memory allocated to the caching layer. So that's a caching layer that has similar properties. But then there, of course, are the full-grown key value data stores that will never forget any values or will never throw away any values, meaning they will start using disk storage to store data on disk so that it can exceed the amount of memory that's available. And examples of that are, of course, for example, Membase or Riak. Then there are document stores. Document stores are different in the sense that they understand the value, so they're able to parse what is being passed into the database. By understanding what it means in reality is you can now do searching and indexing on components of the value. So, for example, the documents typically have to be in some known data format like JSON or BSON, and then you can define queries that access elements of that document to do the search. And examples are Couch or Cassandra, for example. So, with these types of NoSQL databases, you can now scale the data layer just the same way as you've scaled the application layer. So what we see on this graph now is that underneath the application layer, rather than having a monolithic big single server database, you now have an equal tier of data storage servers that equally can be added to and removed from as needed. The data is sharded across those servers, so it's equally spread out across them, and it can be accessed by the application servers in the same way, typically via the key. So once the web server in this case would know the key of the information it's looking for, it will ask the storage cluster, and the cluster will then provide the correct value back to the web server application server. As a result, you now are at a case where you can see how the lines are flattening out now and become linear, just like they were for the application tier. So you see, if you have a cluster of Memcache servers, for example, now the system cost scales linearly because you simply add more of your cloud nodes to the system, and the response times, of course, stay flat no matter how much data is being served, because now data is just served from one node based on the sharding, and those nodes have a constant latency, of course. And so this is really what scaling data in the cloud is all about, and what we're here to achieve. So let's look at a few examples, and I wanted to start off by looking in a bit more detail at a key value store. I already, I think, covered those basics, that it's about a user-defined key, and the value can be anything, it doesn't care, and there will be automatic sharding across. And the system we're going to look at is a Memcache server. It's a product from Couchbase, from the company I work for, and we actually based this on Memcache D. So our developers were the key contributors behind Memcache D. And what we did is we extended the in-memory caching layer with a permanent data store, so persistence of the data, so that we can have more data than fits in RAM, as well as replication to other nodes and clustering. Now, what is key here is that we still retain in this system the in-memory caching layer, so that as a result you get extremely low latency. And you can see in this simple diagram at the highest level how basically can be now viewed as having the disk-based data store fronted with a Memcache D instance for the caching, and then of course you have many of these nodes in your system to spread the data across for that purpose. And by the way, Memcache specifically actually also offers Memcache D buckets, so it can also provide just caching nodes if that's required. It's fully compatible with Memcache D and can be actually a drop-in replacement. So for Memcache, because we have a lot of customers in the cloud, and later on I'm going to talk a little more about some typical examples, but for example, Zynga is by far our biggest customer. I'm sure you're familiar with many of their online games, and they are deploying large amounts of Memcache servers all in the cloud. And so that's a great example to show how this architecture is used to scale data out. One of the key things about Memcache itself is that it's all about being simple. Clustering can be achieved simply by entering IP addresses and pressing some buttons. It can be automated via REST calls if necessary. But our motto is that you should be able, within a few minutes, to create a working cluster. You actually see on the small screenshot, that's the setup wizard, basically. So as a new cluster starts, you create a cluster of one for the first node and then join other nodes to it. It's also important that it's very easy to develop against. Key value stores, by their nature, have a limited vocabulary. It's typically set and get. Also things like increment, decrement, add and replace are there. So there are some more operations in append. But the basic vocabulary, or the basic verbs that are available compared to traditional databases, of course. It's very simple, so it's very simple to use from the application. Specifically, because we are based on Memcache D, we're actually fully compatible with the Memcache D protocol, meaning that all the existing Memcache D libraries that are out there will work against Membase, and this means that languages from Scheme to Camel to Python and PHP and Java and C# and so on, of course, are all supported and have existing libraries to talk to Membase, which makes it very, very easy for application developers to use it, and many applications already have the right interface built in. It's simple to manage. There is a graphical user interface that makes it very easy to monitor the system, which of course is key operationally in order to keep your data healthy. It can also all be automated because all the information is available via REST API, but that allows you to very easily do things like failing over nodes, adding nodes, rebalancing data, and therefore make sure that operationally you can also scale, because of course that's the other aspect, that not just your data needs to scale, you need to make sure that operationally you will be able to manage a cluster of the given size. Speed, low latency is a key, and in Membase specifically, it's very much tuned to that. A typical latency is below a millisecond. That can be achieved because the working set is cached in RAM across the cluster, and as a result, you have our motto is never keep an application waiting, and that's what our customers find. We're actually heavily used in the ad serving industry, for example, where latency just isn't an option because pages need to get their ads, or otherwise no ad will be shown. High throughput is the other aspect, of course. If we want to serve lots and lots of users, you need high throughput as well as low latency. We achieve that by having the data path being fully multi-threaded. There is almost no lock contention, and that is done as part of the denormalization of the data with the key value principle. Another key thing that we have, which plays extremely well for the cloud, is that there is automatic write deduplication. What this means is that you often find that once a key is accessed or written to, in many access patterns, you'll find that the same key will be written to in very short time after, again and again and again. For example, in a game, it might be some user interacting with their bases or something like this, or their farm, and so they will update things, and a lot of update operations might follow in very short succession. In other things, the same patterns are, of course, observed because a user is doing something. Now, I/O throughput is typically one of the bottlenecks in the cloud environment, and what we achieve by write deduplication is that the incoming I/O load through the network does not need to equal the write throughput to disk. And this is achieved by basically if the same key gets updated in short succession, only the latest value will be persisted to disk. And those are tunable parameters within Membase. But it effectively has Memcache D as the memory caching layer, decoupling the system from the I/O throughput of the disk. And that's a great benefit when it comes to other NoSQL databases that are based around straight writing data to disk. And whilst there's, of course, typically some caching from the OS, it doesn't decouple it in the same way, and it doesn't have the deduplication. And our larger customers find that one of the key benefits of using our architecture, because I/O disk throughput is one of the hardest things to obtain and one of the more expensive things to obtain as well. Elasticity is, of course, one of the key benefits in the cloud, but it's hard for applications to use, especially for data stores. In this case, it's around being able to scale the cluster on the fly meaning adding or removing nodes as required. What this means is that there is something called rebalancing that needs to happen. Rebalancing basically means that data is redistributed amongst the machines in the cluster to be evenly spread. And of course, in the case of Membase, you can also create replicas, meaning that the data that's being spread is not just the active data, but it's also some of the replica copies. So all of these need to be spread evenly across the cluster, and that's called rebalancing. And one of the key benefits of Membase is that the rebalancing happens whilst the data is still fully accessible and still accessible at low latency, meaning that you can add and remove nodes as zero downtime operations. We even allow upgrading of systems with zero downtime simply by balancing out nodes, removing nodes from the cluster, and then balancing in nodes with the upgraded software version. So this way you can even do an upgrade of versions with the cluster never being down, never being unavailable. You can use this to implement dynamic rebalancing. So, for example, with RightScale, which I'm sure many of you are familiar with, RightScale has write scripts and provides tools for automatic scaling of system depending on load. So in our case, it means you can simply add and provision additional database, additional Membase nodes that will be integrated into the cluster with an automatic rebalancing taking place to spread the load. And so this way you can grow and adjust your capacity closely to your needs, and of course as a result make sure that the cost for your data storage layer is minimized and is only set depending on the actual needs and demands. In our architecture, all nodes are created equal, meaning that any node can replace any other node. If you remember what we said about the properties of cloud architecture around that, of course, in a cloud system, node failure happens. It's a occurrence that your system will need to be able to cope with. And in the case of Membase clusters, that's easily dealt with. It simply failed over to another node. There are no special nodes, no zookeepers, or any other privileged nodes which failure would cause a problem. All nodes are equal, and any node can replace any other node. And as a result, it also means that from a scalability point of view, of course, you simply have one machine image for a cloud node for the data layer, and you simply can instantiate as many of that as you need. Lastly, we also have a changes feed. So we have the capability to stream out changes. Those can be streamed into indexes or into other systems, and I'm actually going to give an example of that in a few minutes in one of the use cases. Okay, unless there are any questions, let me go on and talk a little bit about some of the use cases so that you can see how other people are leveraging this technology. One of the key areas that NoSQL databases, and especially Membase, are successful in is in the online gaming. You can see how those have many of the properties we just discussed. It's a lot of concurrent users. Low latency is very important. If you play a game, you don't want to wait. So you have massive amounts of data, massive amounts of users, and low latency requirements, all things that traditional RDBMSs just aren't designed to work with. And as a result, the largest provider of online games, Zynga, is actually using Membase as their NoSQL data store of choice. Can show you a little bit about a typical architecture, and you can see on the left there are many other companies in that realm using Membase. And they always have the very simple architecture. It's basically the basic 3-tier architecture I showed earlier, meaning they have the browsers as the presentation layer playing the game. They have the application layer running PHP or Java or C# code as the actual application to provide the game logic. And then underlaying is a cluster of Membase nodes. And Couchbase, of course, is the company. and a cluster of our nodes, and that is used to provide the data and the low latency access to that. And so it's a very simple architecture, but very, very successful and well proven out in customer deployments. Another area where low latency matters a lot is when it comes to the ad offering services. So the ad market, the online ad market has changed a lot in recent times, especially when it comes to real-time ad exchanges and so on. What is happening is that basically a page is loading, and now there is a spot to show an ad in. What is happening is that there are user cookies, or there's an identifier for the user that is requesting the page, and then typically there's information about that user. Typically these providers track which web pages have been visited by that user in the past. And so based on that, you can now decide which ad to show. What this means is that a system comes back with some sort of identifier or cookie about the user, and then in an ad exchange that is provided to many different companies, who then can look at what they know about this person and whether they would like to offer an ad for that person, and then they bid actually on how much they are willing to pay for that ad in real time. And then the winner will be allowed to serve an ad that is displayed on that page. Now, you notice just me explaining this took quite a few steps, and that's no coincidence. There are actually a lot of steps involved, yet at the high level when it comes to the page load, there are typically stringent requirements. So AOL, for example, in this example here, has about 40 milliseconds to respond with a decision at the highest level, but there are lots of other steps involved, which translate down to that the data layer typically have access requirements around a few milliseconds. Now, a single disk read it will be 10 milliseconds at least, so you can see how traditional disk-based systems just struggle or unable to really provide the latency that the ad industry needs. And so this is why quite a few agencies have gone with Membase. Because of our memory caching and the very low latency, it becomes very attractive to access real-time user information or even the ads themselves. Now, one thing that's interesting that AOL is doing, they have talked about this in the past at some conferences, is that you can use this changes feed that I was talking about with Membase to actually stream data out of the data store, out of Membase, into something else. And what some customers are doing are they streaming this into a Hadoop cluster for offline analytics. So as you know, Hadoop is great for MapReduce and for batch analytics, so offline analytics of data. But at the same time, HDFS just isn't, and HBase just aren't optimized for low latency data access, so you can't use the Hadoop cluster itself as the data storage that provides you the low latency and the clustering and all that. But instead, you're piping the data out of Membase into a Hadoop cluster, you do the operations, and then the results are being fed back into Membase for access from the real-time access layer, so from the ad server, for example. And so with this, you, in a way, get the best of both worlds. You get the low latency from Membase for your data access, and you get the full processing capabilities for offline analytics of Hadoop. And so that's, I think, a very interesting use case, and it shows how, in the end, systems like Membase are becoming a building block in larger solutions where you can really combine the various facets that are optimized for that part of the solution. Okay, now let's move on and let's look a little bit at document stores. As I said earlier, it's the next to key value stores. It's the other key type of a database, a NoSQL database that is commonly used. Document stores are different in the sense that this document or the value part that's being stored is now understood by the data layer itself. So it can be something like JSON, for example. Now it's still schema-less, so meaning that all these documents can have a different structure. They just need to have a structure that can be understood. And as a result, we can now build views and indexes of that. They typically have an easy-to-use API interface. And of course, for the clusterability, replication, and distribution is there for scalability. I'd like to look a little bit more at Couchbase Server. So Couchbase, the company I work for, was actually formed by the merger of Membase, who were building the database I just talked about, Membase Server, and Couch1. Couch1 was founded by the creator of CouchDB, Damon Katz, and his team. And so Couchbase Server is Couchbase's version of CouchDB. It's basically a binary distribution of CouchDB with some other features and very conveniently distributed. So Couch itself is proven very widely. It's used by actually probably the most widely used NoSQL database, used by companies like the BBC, for example. It works with JSON, meaning that the documents that are being stored as JSON documents, which of course is a standard, and most programming languages these days are able to handle that just fine. It allows indexing, querying. What is interesting with Couchbase Server is that it's using incremental MapReduce to do that, meaning that it builds up basically materialized views, but then only computes updates to that based on the changes that are happening in the system. It's a very elegant system, and it has a great benefits when it comes to scalability, because MapReduce problems can be divided up very easily, meaning you can take a problem and run it on subsets of the data and then aggregate the results to get the same results as if you had run the MapReduce over the original set of data. So this is going to be very important. And Couch, of course, provides very flexible replication mechanisms. It's one of the leading areas. It has document revisions, meaning that for each document it stores not just the current version, but also the previous versions. And it has ways of, when you now synchronize multiple Couch databases on different machines, it will detect where there is a conflict, meaning where there is basically the same key with different documents, and so it can detect those conflicts. It will automatically resolve them and pick a winner, but it will also store both versions to allow application logic to later on change that, maybe merge the data and so on. So it's very powerful and flexible when it comes to replicating data out. Now, looking ahead, what we are currently in the process of building, so both Membase Server and Couchbase Server are shipping products. We are also combining both products. Right now, the persistence data layer, so the storage to disk from Membase, is handled via SQLite. This will be replaced by CouchDB, and by using now the document store underlying Membase, we basically get the best of both worlds. So we will get the clustering and the sharding and the failover, as well as the in-memory caching layer from Membase. But then we get Couch's document feature, so that we now understand JSON documents, and that we can do querying and indexing on parts of the document, so that it can use this to now do, and this is where the MapReduce scalability comes in. Basically now queries will be partitioned, and each node will run a part of the query, and the results will be aggregated overall. And that resulting product is called Elastic Couchbase, and it will be available later this year. And so certainly, what you heard so far about the properties of Membase and Couchbase, feel free to check in on our website with more news about those upcoming products. Lastly, let me maybe take a step back and try and see where I see the whole data layer in the cloud heading the NoSQL market. What we already are observing is that there is a somewhat a merging of features happening, meaning in the beginning different products had different strengths and would leave out entire functionality areas. There were things that were, pure key value stores, pure document stores, things only optimized for one area, and so on. What we see happening right now is that the requirements in the end that come from the users are very similar, and as a result, the different products start to improve in the areas where they were lacking previously. So the strict key value stores like Membase or React start to add functionality to allow searching and indexing. The document stores start to worry more about clustering and low latency access. The auto-sharding, the whole clusterability, something that things like Redis, for example, never had in the beginning. They were always designed as single value systems, single machine systems. Those are starting to be clusterable and so on. So there's certainly a convergence on a certain set of features. The whole neutrality of the stored value, meaning that what is the key value store, what's a document store, all those things are blurring more and more together, really, partly because of the feature requirements that are, from the previous points, but I wouldn't be surprised if in a year or two, people won't really be distinguishing key value stores and document stores anymore because they'll all become one type of product. And largely, of course, given that the name is NoSQL, some people always are asking whether this means that the goal is to try and replace SQL. And while certainly we wouldn't mind, we don't think that's very likely because there are areas where relational systems are the ones that fit best. And clearly for certain types of data, for certain types of requirements, these are the best fit, they are the best of breed, and there's no likelihood of them going away. Certainly, the areas where NoSQL solutions will increase, both because new data and new use cases often seem to be more focused on the type of data that NoSQL database can do, but also because NoSQL databases, we just said, start to catch up in functionality and searching and indexing and querying, which was hard in early systems, starts to become easier and easier, so that certainly there will be a bit more of an encroachment into the RDBMS space. But overall, we will always see that there will be applicability of the traditional systems, and I wouldn't see them disappear. It's really picking the right tool for the right problem. This is the material I have prepared. I thank you all very much for attending. We still have a few minutes left for questions, so if there are any questions, please go to the right section of your WebEx pane. There's a Q&A section, and if you select all panelists, you can let me know your questions, and I'll be pleased to answer any. Okay, it looks like there are no more questions, so thank you very much for listening in, and if you have any questions, please feel free to contact me. You can contact me at frank@couchbase.com. Thank you very much. Bye-bye.